So let me show you what mine looked like when I did this. So the first problem, everybody should pretty much look the same for this. This is just our theoretical probability. So you've got 6 values on a roll, 1 through 6, and each of those you have a 1 out of 6 chance, which you can always use the decimal also. 0.167, add all those up, probabilities equal 1, so you can always check that too. And then you should have a graph that looks similar to mine. Might not be, that high depending on how you labeled your y-axis, but all your bars are at the same height. It's a histogram, so remember we want our bars to touch. And then this is what we would call either uniform or rectangular. So if you have either of those, that's fine. But pretty much all of our values have the same chance of occurring as what we're seeing in this chart. Okay, questions on that one? Nothing crazy. Okay. So then I did all my rolls, and yours, of course, are going to look a little different than mine. I just rounded mine to 1 decimal place. Then I totaled them up. How many were 1 but less than 2, 5, all the way up to 6, so on and so forth. And then I calculated the probability of each of those occurring based on the experiment that I did. So I took each of my number of rolls, so like 9 for that second row, divided it by 40, how many trials I had, and the proportion of 2s but less than 3s were about 0.225. And 3s but less than 4s, I had 20 of those, 20 out of 40, I had 0.5. And I didn't have to round mine, but you could always round to like 2 or 3 decimal places. And then those 1 to 2, 2 to 3, 3 to 4, those create nice little boundaries then to create your histogram with. Between 1 and 2, we go up to that first value. And actually, wait, something is not right on mine. All my bars should be shifted over 1. Like this bar should be here, this bar should be here, this bar should be here. This one was a 0. I got in the wrong spot. You didn't hit it. The shape is what's important here. Did most of you have something that was symmetric or close to symmetric from what you had? Okay. And it might have been skewed, like mine was skewed a little bit to the right. You can see I have a tail to the right there, kind of goes down a little bit. So yours might have been skewed one way or the other. But you're seeing we have this data set that is not symmetric to start, not a bell-shaped curve. And when we take a bunch of means, if we take a bunch of samples and take the means of those samples, those end up creating this normal curve. Why? Or close to it, okay? And the more trials we do, the closer we're going to get to a normal curve. Why do we care to want to do that? Because if I can make it a normal curve, I can use my z-score chart. If I can use my z-score chart, I can calculate these probabilities, proportions, and all these things that we want to be able to do. But a prerequisite of that is that we have a bell-shaped curve. And if we have a data set that's not bell-shaped, we can use this method to make that happen. Okay, so this is a really big idea in statistics called the central limit theorem, if you want to flip to the back there. So the central limit theorem says, let's say I have any data set that is not a bell curve, not a normal distribution. If I take samples from that population and their means will create a normal distribution. And better than that, the mean of my sample means will approximately equal the mean of the population, which is important. And the standard deviation of my sample means will equal the standard deviation of my population divided by the square root of n, where n is the size of the sample that we took. Now we're going to talk tomorrow about the bigger the sample you take, the better it is. We only had a sample size of 4 in ours. We were rolling 4 die at a time. That's how big we were, how many numbers we were averaging each time. We want that usually to be bigger, but for our dice, it was sufficient to kind of get the point across today. Okay, so make sure you have these written down. The notation that you're seeing here, mean, and then this is like a sub-notation with the X bar. This is not the mean of the population. It is the mean of the sample means. So all those little means you took, we average them together, that is approximately equaling the mean of the population, okay? And this is the standard deviation of the sample means. Again, when you see that little X bar, is the standard deviation of the population divided by square root n, where n is your sample size. Okay, so now let's do the back part together. Let's see if I can make mine a little bit wider. There we go. All right, so we are going to test our theorem out with the formulas, okay? We kind of saw it happen, it did what it was supposed to do with the symmetry. Let's see what happens with the formulas. All right, so this is the chart that you guys have on the first page. We're just going to add another row to it, and you will need your calculator or something at some point here. All right, so my values of the roll were 1, 2, 3, 4, 5, 6. And the theoretical probability of each was 1/6. And I'll just leave the fraction for now is good. 1/6, 1/6, 1/6. Okay. If you remember, if we wanted to find mean, which we had a special word for it with our probability, we called it expected value of a probability situation. It was x times the probability of each x, and then we added them all up. I like the word expected value here because it's what we expect to happen. On average, what am I going to roll on this dice is what this number is going to tell me. What number is going to show up when I roll it. All right, so in the third column, we're going to do each x times its probability. I have fractions, so I'm just going to leave them as fractions because I think that's going to be easier. 1 times 1/6 gives me 1/6. 2 times 1/6 gives me 2/6. And so on and so forth. 3/6, 4/6, 5/6, 6/6. And now to find the mean, or the expected value, we add all of those up. Maybe you can do this in your head. What's 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6? How many 6 do I got there? 21/6? Is that right? 21/6? About? Yeah? Okay. And then 21/6 will give me approximately, we're going to see a decimal here, 3.5. Actually, it's exactly 3.5. That's nice. Okay, so this is saying on average, if I roll a die, the value that comes up is going to be about a 3.5. Now, did you guys take all those sample means you had, put them in your calculator, and get the mean from that? What did yours say the mean was from all 40 of your data values that you collected? What was it? It was 3.48. 3.48. 3.34. 3.74. 3.74. Are we seeing a pattern? What if I took all of your means and I averaged those together? We had some 3.7s, we have some 3.2s, we had some 3.3s, law of large numbers, right? Says if we take all these numbers and keep putting them together, we're going to get closer and closer to that value. And if we had taken bigger samples, we would get closer than that. So whatever your mean was, put that there. Okay. I think mine was slightly under. I think mine was close to like that 3.48 that you had. And then part C, how do they compare? They should be approximately equal. Okay, and that's that formula. If we have the mean of the sample means, it is approximately equal to the mean of the population. Okay. Question so far? Okay, all right. So this is super useful, and we'll watch a little video on this probably tomorrow, I think. If you are not able to calculate the mean of a population, which usually we are not able to because they're so large, we can take samples and find the mean of those, and the mean of those values is going to be approximately equal to the mean of the population. So it's a great way to estimate things. All right, let's do the same thing this time, but we're going to calculate standard deviation. All right, so it's going to start out looking the same, the value of my rolls, and I left an extra row at the bottom here for you to sum those up. Okay. Theoretical probability of each was, again, 1/6. 1/6, 1/6. Okay, the formula that we are using, again, we used this in the last chapter when we did probability, is over to the side there. This is the variance formula, and we know once we have variance, we just take the square root of it to get standard deviation. But these are the steps that you guys used on your chapter 4 test. Remember, you made that big chart to calculate standard deviation. So we did x minus the mean. Now here, if I do x minus the mean is 3.5. Okay. Then we're going to square it, x minus the mean squared. And then we're going to multiply it by its respective probability. Okay, but again, we had that mean from the previous problem. All right, so each x minus 3.5. 1 minus 3.5, negative 2.5. 2 minus 3.5, negative 1.5. 3 minus 3.5, negative 0.5. 4 minus 3.5, 0.5. 5 minus 1.5, 1.5. 6 minus 3.5, 2.5. Take those and square it. 2.5 squared, 6.25. 1.5 squared, 2.25. 0.5 squared, 0.25. And those guys at the bottom are going to be the same because I'm squaring it. Doesn't matter if it's positive or negative. 6.25. Okay. Now we're going to take each of those deviations squared, multiply it by 1/6 because all the probabilities are the same. So 6.25 times a 6, or just divided by 6. I'm going to round to, I'm going to give it 3 decimal places. 1.042. 2.25 times a 6th. 0.375. 0.25 times a 6th. 0.042. And then, again, we've got those same values times the 6th again, so we're going to see our table is symmetric. Those values are going to repeat. So 375, 1.042. At the bottom, the sum is going to give us our variance, our sigma squared. All right, so 1.042 plus 0.375 plus 0.042. And I have 2 of each of those. I get a sum of 2.918 is my variance. If I want to take it one step further, if my variance is 2.918, we know we're going to take the square root of that and get our standard deviation. So if the expected value or expected roll of a die is about 3.5, the expected standard deviation is about 1.708. Okay, the central limit theorem says our standard deviation is not going to be exactly that. It's going to be that divided by the square root of n. And in our problem, n was 4 because each sample consisted of 4 rolls of the die. So we're going to ultimately just divide this by 2. So I get approximately 0.854 is what our sample data should have a standard deviation of. Okay, now I'll show you what mine was. I think I had it on here somewhere. Maybe. I'll zoom in on that in a second. Mine was 0.828 when I did it. Okay. Again, you guys calculated these with your graphing calculator. Was yours close to 0.8 or 0.9? Was it in the realm somewhere? No? Yes? Maybe? What do we get? What do you get? 8.55? Ooh, that's a big standard deviation. Oh, 0.8. Okay, that's that. I was like, woo! That's a lot. Yeah? 0.962. That's a little big. Okay, but it's within a 10. 2 tenths maybe. Yep. Okay, so here's a little, so we average yours together, we're right there, right? Okay, you guys kind of seeing the pattern here? So somebody figured out we can do this with large sample groups, a lot of samples, and we can get really close to figuring out what that actual mean and standard deviation are. Do you see how this would be like super useful in statistics? If we have a population of like 1 million things and I can't actually survey or calculate all those million things, I can take a bunch of samples and calculate the data from the samples with their means and figure out that information I need for the large group. Okay, so tomorrow what we're going to do, you guys can just tonight keep working on that 5-2-5-3 homework stuff. Tomorrow we're going to watch a little 7-8 minute video just kind of like showing how we would use the central limit theorem in real life. And then we're going to do some problems where we're actually using the central limit theorem to do some calculations. Okay? All right. All right. What do I got? 17. Anybody in there? Yes! What's the number 17? Anybody want to claim it? Okay. All right, last 5 minutes are yours. You're welcome.